Extreme values of continuous functions. And I think we decided our test goes through this section. Is that correct? On Wednesday, I just put the review sheet up. It's 3.3 through 3.8, and now this one, 4.1. On to chapter 3, second first two sections. This one. So we said that if we have, if f is continuous on the closed interval from A to B, then f attains both an absolute maximum and an absolute minimum. And we saw where they would occur. The extreme values will occur at some critical number within the interval, where critical number was a value of x at which the derivative is 0. Or it might occur at one of the endpoints. Candidates are critical numbers in the interval and the two endpoints. A and B. We just make a list of these critical numbers where, again, critical number f prime of C is 0, and C is a critical number. Not just where it equals 0, because we might have a continuous function that has some of these sharp corners in it. And if it has sharp corners, then a critical number could also be where the sharp corner occurs, and that would be where there's no derivative. So does not exist. So we did like polynomial type examples. We did one trig example last time. Let's look at so let's do polynomial again, and then we'll go on to another type of example. T polynomial function t to the fourth minus 2t cubed minus 12t squared plus 60t I want to find absolute max, absolute min on the interval, I think from 0 to 3. Good. Have something that's not going to factor. We'll find out. Yeah, let me make an adjustment.
Put 60 on the fruit.
48.
Yeah, the factor, factor 6.
That's gonna be a 24. That'll be a 2, but that's gonna be 4 and a 6.
Oh, wait, no, it's 24 times 60, 70.
You know, because this is gonna have a 6 and this is gonna have a 4. If I did that. Make that a 4, I think. Check now. That's a 4. That'll be a 12. Pull 4 out. And that leaves 3. 24 times 3 is.
72.
Let's try that one. I might make further adjustments. I might need to make my interval bigger. So let's go 5. 0 to 5. Maybe. It's Friday. If anything works on Friday, it's a miracle. Okay, so we recognize that it's a polynomial, so we know it's going to be in our category of continuous functions. So all we can do is see if we can take the derivative of that and factor it. If not, I'll just make more adjustments to it. But I think we can. So here we go. Here's the derivative. We get 4t cubed minus 12t squared.
Like the sine sequence, either 12 and 72 or the 2.
I've got a minus here. I think that'll help.
Oh, yeah.
So minus 24t plus 72. And so when I was messing with that stuff, I was going to see if we're going to get a third degree polynomial here. And one of the ways you can factor something like that is by grouping. We're going to set this equal to 0 and try to solve for t. So what I want to do is group these two together and pull out the greatest common factor. Group these two together, do the same, and see if I have a common factor after I do that. So let's set the derivative equal to 0. And do this factoring thing. So the greatest common factor here is 4t squared. And then I have a t minus 3 as the other factor. The greatest common factor here is a negative 24, actually 24, but I'm pulling out a negative 24. And that does change the sign here. And we said 24 times 3 is 72. So there's what I was working on, getting that factor of t minus 3.
Well, I do 24 would become plus 24.
Because if I multiply this out, then I get that. And multiply this out, I get that. So I'm okay with the sign. So we got one more step in factoring, and that's pull out the common factor of t minus 3. So I'm going to have my t minus 3 out front, t minus 3 out front. And then the other factor is 4t squared minus 24. See how I did that? This should also factor as the difference of squares. That's not a perfect square, so that's kind of a bummer. Let me pull out a 4. But I can think of this as being t minus the square root of 6 and t plus the square root of 6. So let's see, square root of 6 is pretty big, huh? Square root of 6 is bigger than the square root of 4, it's smaller than the square root of 9. So it's in that interval. Set each of those factors equal to 0 and you get t is equal to 3. T is equal to the square root of 6. And t is equal to negative square root of 6 as your critical numbers. So both of these are within the interval. This one's not. I can throw away the negative root 6. That's too bad. That's too bad. I got to stick those numbers now into F along with the two endpoints. Endpoints are 0 and 5. And we've got to plug them in to here, into the original expression. Only these guys right here. Okay, so let's start with 0. 0, negative 10. Got that one out of the way. All right, here comes that coffee headache. I'm gonna run back and get it. Uh-oh, gotta move my screen over. I'm coming, I'm moving it over. There it is. I'm taking all my critical numbers and my endpoints and plugging it into that big thing. All right, so here goes 3. 3 to the 4th is 9 times 9, that's 81. 27 times 4 is 108. 9 times 12 is also 108. Then 72 times 3 is 216. So let's see. Look, there's 216. Life is good. 81 minus 10 is 71. Wow. I'm going to go with the 5 next. I'm going to save this one for last. 5 to the 4th, 25 times 25 is 625. 5 cubed is 125 times 4. What's that? Yep. And that was this one. 25 times 12. 10 times 25 is 250. 2 times 25 is another 50, so that's going to be 300. 72 times 5 is 360 minus 10. So I have 6,985 minus 800 is 185 minus 10 is 175. Somewhere in the neighborhood. All right, here comes the yucky one. Let's see, square root of 6 to the 4th is 36. Let's see, square root of 6 cubed is 6 times the square root of 6. So that's minus 24 times the square root of 6. That squared gives me 6 times 12 is 72. And there's plus 72 square root of 6 minus 10. Where am I looking?
36, 72, 10.
How much is it? So that's negative 36, negative 46. And that's 72 minus 24 is
48.
8 square root of 6. Okay. that's gonna be a positive number. I don't think it's bigger than 175 is my guess. And that's the only negative number. So this one's the absolute max. And this one's the absolute min. So the steps are kind of easy, just a bunch of numbers, I suppose. But let's make sure we can do the calculus part. Let me give you a cube root function. Let's do the same thing. F of x is x to the 2/3 times 5 minus x go on the interval from -1 to 5. Should get two critical numbers. One of the critical numbers is an endpoint. Multiply it out and then take the derivative, or you can do the product rule. Which way are most of you doing it? We'll find it out first. All right, then I'm going to do the product rule. So it's the first times the derivative of the second. Derivative in here is just -1 plus the second.
-1 for negative x.
That makes it hard.
Yeah.
All right, bring that power down, raise that to 1 power less. Okay, instead of multiplying this out, I'm going to rewrite this so that this negative exponent term is underneath this term. So I'm just going to write that as a negative x to the 2/3 plus 2 times 5 minus x over x to the 1/3. Oh, the 3 as well. And now I'm going to put these two together by getting a common denominator. I'm going to multiply this by 3x to the 1/3 over 3x to the 1/3. I'm going to combine them by getting a common denominator. There's the common denominator. We'll multiply it out here. When you multiply like bases, you add exponents. So when I multiply that out, I just get -3x. Now I'm going to send the 2 through the parentheses. I'm going to share that denominator. And I have plus 10 minus 2x. And then when I put those x's together, I have that my derivative looks like minus 5x plus 10 all over 3x to the 1/3. I wrote it like that to show you what it looks like when there is a place where the derivative doesn't exist. You get a factor on the bottom, there's no derivative where that factor is 0. This factor is 0 when x is 0. So f prime does not exist when x is 0. F prime is 0 when the top is 0. What value of x is that? So if you think about why this doesn't exist here, if I had an open interval, which I do, I have it on -1, 5, the graph there either is going to become vertical or have a sharp corner. Well, this is next to the 2/3. It's got a sharp corner there, but you don't know that. I just know it. You'll just have to believe me. That's right. This was continuous. Cube root squared, x to the first power. There's nothing in here that makes this break apart. So I've got a place where there's no tangent line, but it's still a critical number. 0 and 2 are both in that interval. So I take the values of the function at those 2 points, compare them to the values of the function at these 2 points, and then make our decision. Two critical numbers, 0, 2, and then the 2 endpoints, -1 and 5. So we're plugging them into F. Let me write it here so I don't have to keep looking up there. That's a 2/3 power, so I can take the cube root and then square the number. But 0 to any power is 0. So 0 times that is 0. And then the 5 is going to do the same thing. 5 makes that factor 0. So here it's 0. So when I put a 2 in there, I have a 2 to the 2/3 times 3. And I can write that as the cube root of 4, since 2 squared is 4. Cube root of 4 times 3. When I put a -1 in there, the cube root of -1 is -1. Squared is a +1. So -1 to the 2/3 is 1. 5 minus a -1 is 6. So my only question is, do I think this number is bigger than that number? You think it is? I would think that the cube root of 4 is smaller than the square root of 4. right? Square root of 4 is 2, 2 times 3 is 6, cube root of 4 is going to be smaller. So this is smaller than 6, which makes this the absolute max. And the 0 is the absolute min, and it occurs twice.
Can you explain where you got the x equals 2 again?
At the top equals 0?
Oh, you just did the top.
Yeah, because that's what makes the fraction 0. The fraction is undefined in the bottom is 0.
So you can set either one equal to 0.
You have to set all your factors to 0. Okay. All right, we can do the functions. You can tell me if it's continuous or not. I'll move the screen over, so let me write it down, then I'll move it over. First is continuous. Let these guys in on the game here. Going back to the east. So I've got a piecewise defined function. Looks like a straight line segment 8 minus 2x when x is a number smaller than 2. And it has that piece of the parabola when x is 2 or more. And I want to just look at the function on the interval from 0 to 4. And so my first question is it continuous there? So I know this looks like a line, that looks like a parabola. So when I don't worry about that, I know those pieces themselves are continuous. We have to make sure that they hook up when x is 2. Do they? I put a 2 in the top, I get 8 minus 4 is 4. Put a 2 in the bottom, I have negative 4 plus 8 is also 4. So it is continuous there. So we need its derivative. F prime is negative 2. If x is smaller than 2, it's negative 2x plus 4 if x is greater than or equal to 2. I didn't want that to happen, but it did. So this part's never 0. Negative 2x plus 4 is 0 when 4 is equal to 2x or when x is 2. So I have one critical number. The joining point would have been a candidate anyway, because that's where the graph has a sharp corner. So I have that critical number and the 2 endpoints, and we're going to plug them into F. But make sure you plug them in the correct places. I got 0, 4, and 2. So what's f of 0 going to be? What's f of 0? It'll be 8, right? 0 smaller than 2, so I put it in here. 8 minus 0 is 8. What about f of 4? I have negative 16 plus 16 is going to be 0. And then f of 2 is, so this one's your max. That one's your. Okay.
Did you put them into both of those?
Nope, I plugged it in where it belongs. Why can't I plug x is 4 in here? That says it doesn't belong in there. I have to plug x is 4 in here. I plugged x is 0 here because it doesn't belong there. Has to be part of the plug.
Two goes in one.
That's right. That's right. That's right. Okay. Okay, so now consider a function on an open interval. Any continuous function on an open interval. We take that away. We're no longer guaranteed that this function is going to have both a max and a min. What I want you to do first is draw a function that has an absolute maximum, but no absolute minimum. That one? There are lots of them. Upside down problem, right? Because the ends keep going on. It's got no min, right? And so if I ask it the other way, draw a function that has an absolute min but no absolute max, you just turn it around. Is it possible to draw a function on the open interval that has both an absolute maximum and an absolute minimum?
Sorry.
Good.
The limits count for doing those.
What do you mean?
Like if there's a horizontal asymptote,
Sure.
that's.
But we want continuous functions, is what my point was.
I mean, yeah, horizontal.
So, yeah, so you
So
could
if it
have
goes
drawn
on
me,
forever approaching forward, which will be a limit.
yeah, you could have drawn me something here where the ends, right? That has a max and a min, and then we have some sort of asymptote in between. The sine of x does the same thing. Right? So it's possible that a continuous function on an open interval can have both. It could have one. Can you draw me a function that has neither an absolute max nor an absolute min? Again,
Y equals X.
y is equal to x, has neither an absolute max or min. Good, good. But the fact that it's on a closed interval cuts off the endpoints, cuts off the arrows taken off. Right? Okay, so the idea is easy. If be able to implement the idea and crunch numbers without enough caffeine. And so I want to go on to section 4.2, something else that's very easy. Mean value theorem and Rolle's theorem. What we're working toward in this chapter is hunting for critical numbers and what they're going to mean to us about the function. So we've seen on a closed interval, the critical numbers could lead to possible extreme values. And on an open interval, the same deal. Our extreme values are going to occur at critical numbers. The mean value theorem is something that's really kind of obvious. When we talk about mean, that's the mean that's not angry and rude to you. That's average, an average value. So if you take some sort of function that's continuous and defined on a closed interval, and not only we're even going to go to the category where there's not going to be any sharp corners in there. So it's going to be a continuous function and a differentiable function. So there's no place where the derivative is 0. It's going to be continuous on the closed interval and differentiable on the open interval because the derivative at the endpoints never exists anyway. We're going to call the mean value of this function the slope of the line that connects the two endpoints, because I'm cutting it off on a closed interval. So that's our mean value. Our mean value is y2 minus y1 divided by x2 minus x1. I'm going to draw something here. There's a continuous function. Let's split a and b to be. That's x is a. X is b. So if I connect those 2 points with a straight line, I expect the line to be really straight with no coffee in me. But that line there has a slope that's given as the mean value. And what the mean value theorem says is that this function is going to have at least one more place somewhere between A and B where the slope of the tangent line is parallel to that blue line. That's all this theorem says. Somewhere in here on this curve, the slope of the tangent line, maybe here, is parallel to the slope of the blue line. At least one time. So if f is continuous on AB, differentiable on AB, then there is at least one value in the interval A to B, for which the slope of that line that I drew in blue is equal to the slope of the tangent line at that point C. It can be more than one. This is called the mean value. The slope of the line that connects the endpoints. So in the picture that I drew, trying to go through this again, we see where that would be. Maybe about right here. Is it parallel? This theorem isn't terribly useful to you. It does pop up inside of derivations of some other things later on. When we talk about arc length in calculus 2, we cut our intervals up into little pieces. And some we get expressions that look like that. And then we can say, well, by the mean value theorem, there's somewhere in there that's roughly the derivative. And so you'll see that this shows up in the formula for finding the length of an arc. It shows up in the middle of a lot of proofs in, I don't know, where's my math majors in here? You got any math majors in here? When you're in advanced calculus and you get stuck on how to prove something, pull out the old mean value theorem. That might help you. Somewhere in there you need a derivative and you just can't figure out how am I going to get that derivative in there. Well, let's try the mean value theorem. All right, I'm going to show you how it works, and then I'm going to rag on Rolls. This guy here took this theorem, put his name on it by having the special case where these two y values are the same. What? This guy said, well, suppose at the endpoints, f of b is the same as f of a. Well, then this numerator is 0. And that says that there's some critical number in the interval. And he said, boom, I'll put my name on that one. So, Rolls theorem. Is that using those same conditions, f is continuous on the closed interval, differentiable on the open interval, but adding one more. Now, if f of b is equal to f of a, we have, ooh, I can't write anything. We have that is 0. We have that statement. So there is some critical number in the interval from A to B, open interval. That's how Rolls theorem says. Two y values are the same, and you know there's a critical number in there. So what we're going to do is look at some examples and see if we can find that number C that's guaranteed by these theorems. I have to move forward, so we'll write my example and then I'll move forward. Any of my examples with me? Let's do an easy one. There's your polynomial. F of x is x squared plus 3x minus 6. That's as continuous as they come, just a little parabola. Find the value of c in the interval, oh, I don't know, let's go from 1 to 4. Guaranteed by mean value theorem. So we first point out to the world that because that's a polynomial, we know that it's continuous and nice and smooth, and so it has a derivative rather than that. Since f is a polynomial, it is continuous and differentiable. Not just on that interval, but everywhere in the world. Okay, so now what we have to do is find the slope of the line that connects the two endpoints. Our endpoints are 1 and 4, so we need f of 4 minus f of 1 divided by 4 minus 1. So we're looking for the value of c satisfying slope of the line through the endpoints is equal to the slope of the tangent line. That's what we're looking to solve for c. Let's apply our function here. The derivative of this feller, and that is an acceptable pronoun because this polynomial said it goes by feller. Politically incorrect polynomials. That's 2x plus 3. So f prime of c is 2c plus 3. Now let's get f of 4. F of 4 is 16 plus 12 minus 6, 22. F of 1 is 4 minus 6 is a negative 2. And 4 minus 1 is 3. There's an equation for us to solve.
You put C because it's continuous, so you just.
Yeah, because I'm looking for that guy. I'm looking for it.
So you just took the derivative of
I
f,
took the derivative and evaluated the next to c.
and it's at points.
So it says find the value c that makes that equal to that number. Following the recipe. Step 1, find this. Step 2, find that. Now set them equal to each other. So the left-hand side simplifies. Let's see, numerator is 24 over denominator 3. 24 over 3 is 8. 8 is equal to 2c plus 3. Subtract 3 and I get 5. 5 halves. And that's certainly in here. So we said there would be one. There could be several, but in this case, there's only one. Okay. make it short as well. Let's do the same. Does f of x equal to 1 over the square root of x on the interval from 1 to 4? 1 to 4 satisfy criteria. Ooh, I can't spell that word. Criteria. Or the mean value theorem. This is continuous on the interval from 1 to 4. Is the derivative defined everywhere on the interval from 1 to 4? The only problem spot would have been 0, and that's outside the interval. So, yep. Then find that value C, guaranteed. Oof. Promised. By the mean value theorem. Find the value of C, where the derivative of that function is equal to the slope of the line through the endpoints at 1, 4. F of 4 minus f of 1 divided by 4 minus 1. So let's see, we need f prime. Write that as x to the negative 1/2 and take the derivative. Here, f prime in terms of x is negative 1/2 x to the negative 3/2, right? And I can simplify that by moving the x to the 3/2 to the bottom and making the exponent positive. All right, so now what we need is what it says. F of my interval 1, 4, f of 4 minus f of 1 over 4 minus 1 has to equal that derivative when x is replaced by c. F of 4 is 1 over the square root of 4. F of 1 is 1 over the square root of 1. 4 minus 1 is 3. So I have a 1/2 minus 1 in my numerator. 1/2 minus 1 is a negative 1/2. And I divide negative 1/2 by 3. Fix that. Make that prettier.
Get the negative 1/2 again.
That's a 1/2 minus 1.
So not the radical.
Square root of 4 is 2. Square root of 1 is 1. So 1/2 minus 1. All right, who's got negative 1/2 divided by 3 for me? Negative 1/6. Flip that over. Multiply. Yep. Cross multiply here. Cancel the negatives. Give you 2c to the 3/2 is equal to 6. Divide by 2. Now what? All right, give her that kooky power.
to square the three.
Okay, square both sides. Raise the power to a power, you multiply exponents. I get c cubed is 9, and now I take the cube root. Cube root of 9 should be bigger than the cube root of 8, so it's 2-ish. 2-ish is in there. It said be a nice number. Just said there's going to be something in here at which the derivative is the same as the slope of the line through the endpoints. Okay. All right, let's do a Rolle's theorem. As Rolle's theorem apply to f of x is equal to the sine squared of x on minus pi halves to positive pi halves.
Right.
Does Rolle's theorem apply to f of x is the sine squared of x on that interval there? So we have to check if the sine squared is continuous on that interval, if its derivative exists on that interval, and if the y2 minus y1 is this, if y2 and y1 are the same on that interval. So, what makes you think that this is a continuous function? The square helps, but the sine itself is continuous. And the operation is done on a continuous function that keeps it continuous. So f is continuous on that interval. Its derivative is what? The derivative of the outside, which is the power, times the derivative inside, which is the cosine. And so that exists everywhere. So that's continuous on minus pi over 2 to pi over 2. So it's differentiable. Say that, let's just say is defined. And so now we have to check what the value of this function is at the two endpoints. So let's compare f of pi over 2 with f of negative pi over 2. If they're the same value, then we can use Rolle's theorem. So I need the sine of pi over 2 and then square it. And I need the sine of negative pi over 2 and then square it. One in negative 1, one in negative 1.
If you square negative one, that should come one.
Yep. So Rolle's theorem does apply. F of B is equal to F of A. So check on that one, check on that one, check on that one. So the answer is yes. So now let's find that value of C at which f prime of C is equal to the derivative. There's at least one critical number in that interval. Let's find C for which f prime at c is 0 inside the interval negative pi over 2 to pi over 2. So there's our derivative. We set it equal to 0 and solve for x and say that that's our c.
Well, that's factored.
Yeah, it's already factored, set each factor equals 0 and solve for x.
So
Where in this interval is the sign 0?
that's 0.
That's 0. What about this?
Negative pi over 2 pi.
They both at the pi halves, right? But those are endpoints. Rolle's theorem says there's something inside the interval. So that's the value of c satisfied by Rolle's theorem. All right, some implications of this. Let's see what the two implications are. Suppose f is continuous on AB with f prime of x is 0 for all x in AB. What do you know about f? Yeah, it's like a horizontal line. What's the equation of a horizontal line?
I equals something.
As equal to a constant, right? So this is saying that f is a constant on that interval from A to B. And have a horizontal line portion in order for its derivative to be 0 everywhere. Okay. So what we just did is our first antiderivative. We have a function whose derivative is 0. What was the function? There it is, our first antiderivative. Antiderivative of 0 is a constant. All right, next one. Suppose f and g are two continuous functions. On the interval from A to B and differentiable. On the open interval with f prime equal to g prime for all x in the interval from A to B. What must be true about f and g? You got two functions that have the same derivative. Two functions that have the exact same derivative.
So they'll look like each other, but they don't necessarily have to be on top of each other. They can be spaced out by C.
They can be spaced out, they can be parallel to one another, right? So it says that that's our conclusion, right? One could be up here, one could be down here. Right? That could be F, that could be G. It's just a constant difference between them. So that's what that says. Then F and G differ by at most a constant. In other words, f of x has the same formula as g of x, give or take the number added to it. Y is equal to x squared, and y is equal to x squared plus 5, both have the same derivative. That's what that says. And so again, we'll use that when we talk about anti-differentiation. We get the general formula for the antiderivative, tack on an arbitrary constant so that we can get them all. But those are all both results of the mean value theorem. Nothing startling, nothing stirring. It's just there. And it kind of squeezes in between all the fun stuff in this section. The fun stuff is, here's a function, find all its critical points, and then tell me stuff you know about the function. Right now, we know is that those critical points could possibly give us an absolute max or min if we have a continuous function on a closed interval. Throw away that business about the closed interval and open it up for the entire thing. We're going to use the derivative being 0 to tell us where the tangent line is horizontal, or where the derivative fails to exist to tell us where the tangent line is vertical, and then use it to describe regions around that graph. So that's what we'll do in section 4.3. Got 5, 6, 7 minutes if you want to do some homework problems.
Is this, is 4.2, is this gonna be on the exam as well?
Our exam goes through 4.1.
Okay.
This is where our second test will start.
I have a question, takes some stuff we've already done, and I just need to validate that consistently.
How to do anything consistently, right? Practice, practice, practice. Right? Find out where you keep making the same mistake over and over. Is it algebra? Is it messy handwriting? Is it distraction? Right? What makes you more efficient at something? Nobody wants questions. You just want to get the heck out of Dodge.
I have one. Weird factoring one.
A weird factoring one. I'm here to do weird factoring. Okay, well, I've got some papers up here before you leave. Grab your papers. Didn't take you 2 days to learn. All right, let me rub that board off. So I want you to get caught up on your web work, and any write-ups that you're missing, write them up for me, even if they're from way back when. And go through the review sheet. I just posted it this morning. It's not for me, huh? Is that in there? She gave me some. Yes, you did, with this pretty pink handwriting. You gave me 2. Find it?
Yes, I'm almost there. That's
Yes, I got it. Marley, Darren, Ivan, come get your homework on stalling for the homework question. Oh, now I can't see this one. Hannah wrote big enough and Grace. I gotta get my glasses on. Ah. Just in my eyesight, are you? Come on, Keaton. Thank you guys.
for some reason the internet's not working, but I think I remember it. It
Okay.
was 4x cubed
minus 51x².
Woo-hoo.
Let's see, plus 210x
Good freaking night.
minus 275.
And you want me to do what with this?
Factor.
Factor it. What? I mean, this just popped up in your line?
That was on the web work, yeah, number 2,
And this says factor me.
pretty much. I think the original equation was f of x equal to x minus 2, x minus 5.
Oh, then I'd rather do it that way and not multiply it out. You said f of x is x minus 2 times x minus 5 cubed, and you took the derivative? I just take the derivative. I'm going to do it in factored form because it's hard from here. All right, let's do the product rule. So here's the first times the derivative of the second. Derivative inside is 1. Plus the second times the derivative of the first. What's the derivative of the first going to be? Just a 1. And so we're going to set that equal to 0 and try to solve for x. So I'm going to factor from here instead of multiplying it out to there. Because from here, I can see that these two terms have a common factor of x minus 5 squared. Put the 0 here and pull out the x minus 5 squared. So I'm pulling all of these out. That leaves me 3 times x minus 2. And if I take x minus 5 squared out of that last factor, what's left? It's the x minus 5. And so these parentheses are holding that 3. Let's distribute the 3. So I have 3x minus 6 plus x minus 5. And then we're going to have it factored right here. 3 plus 1 gives me 4. And minus 6 minus 5 is 11. So multiplying it out is a bear. But you could have tried synthetic division using the little factors of 275 divided by factors of 4 are possible zeros. That would have been fun. That would have been a pre-calculus problem. Thank goodness we're not in pre-calculus. Try to do factoring even when you're doing the quotient rule. A lot of times you have terms like this. Instead of multiplying it out, try to pull out common factors first. Okay, I'm glad you brought that up. Because it used the remaining time and I'm not letting you out early. I got to spend every possible minute with you today. Yay. Yay. All right, well, have a good weekend. Because they're endpoints. We were looking for one in between because the theorem has open intervals. So that endpoints don't count as candidates. For well, no, they're closed up there, but the mean value theorem and the Rolls theorem guarantees that there's a seat inside the interval, away from the endpoints.
Have a quick question.
Okay.